Hey everybody, and welcome to yet another video, trying to flip the script a little bit and talk about some chemical concepts that you're reading about and we're trying to make work as we are currently remote, and maybe we're going to use in other years when we're not as remote. This one will kind of continue our last two videos, which talk about the conceptual process of dissolving, dissociating, the underlying principles of Coulomb's law that sort of determine the outcomes of those processes. And this one is sort of the idea that once you've got these ions that have dissociated floating around in water, what happens when those ions begin to move around and hit each other? So wanted to talk about this idea of precipitation reactions. So what we'll talk a little bit about at first is just the general idea of how that works. We'll watch a video of how that looks in a somewhat macroscopic view, and then we'll talk maybe about some example reactions and some related ideas, and we'll start heading towards the next practice of this concept, which is to be able to write out net ionic equations, which kind of show what ions are actually forming precipitates and which ones are simply floating around as ions dissociated and not connecting to anything. So the first idea simply is what we're talking about then is dissociated ions that are, as I mentioned, just bouncing around in an aqueous environment. And we talk about that as an aqueous phase. And some of those collisions are going to produce particles, and those particles are going to, if all goes well, they're going to be particles with sufficiently strong Coulombic forces, or maybe we could talk about them as ion-ion forces, to prevent water's dipole sort of forces from pulling them apart. So they're sufficiently strong Coulombic forces that water's dipole forces can't separate them. Or they can't overcome. So this is then these particles that have these strong Coulombic forces, these strong ion-ion forces, will allow the particles to stick together. Water can't pull them apart. And so what you see are these particles with these strong forces forming a solid. So that solid is what we call a precipitate. And so the idea of a precipitation reaction is that you put two aqueous mixtures together filled with these ions simply bouncing around, and that they're all going to start colliding with each other. Some of them repel each other. Some of them are going to be attracted electrostatically. Some of those electrostatic attractions are not strong enough and water pulls them back apart. Some are strong enough that water can't pull them back apart, and then we get this formation of a precipitate. And so those precipitation reactions should look a little bit like this, if I can get this to work. So you'll see the formation of these precipitates. They are listing those in bold. So we get this precipitate. You'll notice it kind of changing colors as it slightly is modified in its formula with the release of SO2 gas. Barium sulfate, an incredibly insoluble compound. It's actually so white and so dense it's used as a contrast medium under radiographic scans. Silver chromate, obviously a pretty cool color in that one. Obviously they've amplified the sound here a little bit. And this is kind of a cool precipitate. A lot of the hydroxide type compounds form these kind of gelatinous things, and there's also this concept of what's called a complex or coordinate ion that's forming that allows different versions of itself to form. So that is this idea of just seeing what a precipitation reaction looks like a little bit up close, certainly at a different speed. And we'll kind of talk about that a little bit more as we go through this. So what's happening from a chemical reaction, chemical equation perspective in a reaction like that? So let's look at an example. Let's say that we're adding something like potassium sulfate to a substance that is also aqueous and is theoretically capable of making a precipitate with it. So let's say that we have iron 2 chloride. We want to know, well, what might they make? The first thing to kind of understand at the beginning level is that when you write an ionic substance and put it in the aqueous phase, that means that it has already dissociated. So what you're really writing, while you write the formula this way, when we start talking about, as I mentioned earlier, these things called net ionic equations, what we really have are separate ions from each other. So the K pluses, you have two separate K pluses that are aqueous, a sulfate that's aqueous, an Fe2 plus that's aqueous, and some Cl minuses that are aqueous. So there's really four different ions bouncing around in there. And there's a few logical things that we can apply here, and we should relatively quickly get to a point where we don't have to worry about this a whole lot. But obviously some of these interactions are not worthy of our notice. So when we have ions that have the same charges coming near each other, those are just going to repel each other, and they're not anything that we need to worry about. So we're not too concerned about those. We're also not too concerned about the interactions between things that we already know don't do anything, because we know that K plus and SO4 don't do anything. We know that Fe2 plus and Cl minus don't do anything because they already didn't do anything, and that's why they ended up being aqueous in the first place. In other words, if K plus stuck to SO4 2 minus, it wouldn't be aqueous in the first place. And so when K plus runs into SO4 2 minus, it doesn't form a precipitate because it couldn't in the first place. And again, that owes to Coulombic forces and their attraction not being strong enough to prevent water from pulling them apart. That only leaves two possible collisions that are something that we should pay attention to. And those two collisions would be the possible collision of K plus and Cl minus, and the collision of SO4 2 minus and Fe2 plus. So let's think about those a little bit logically, and then as we kind of go through this and we talk about net ionic equations in the next video and a little bit in this one, we'll talk about this concept of solubility rules and how it applies. So our two possible outcomes would then be KCl, and we'll pretend like we don't know the state of matter, and FeSO4. We don't know its state of matter. And notice that those actually balanced out nicely in terms of the charges, SO4 being 2 minus, Fe2 plus being 2 minus, K being 1 plus, Cl being 1 minus, so they worked out nicely. Obviously, there are going to be occasions where that is not the case, and you'll have to manage the subscripts to make sure that the charges of the compound balance. So what state of matter might KCl be? What state of matter might FeSO4 be? For the vast majority of the reactions that we're looking at, there's only two options, aqueous or solid. That's what makes this a precipitation reaction. There are some possible liquids that form, some possible gases, but for most of the ones that we're going to do, and certainly early on, it's either solid or it's aqueous. So what might make KCl aqueous? What might make it solid? Well, stronger Coulombic forces are going to make it more likely to be solid. Weaker Coulombic or ion-ion forces are going to make it more likely to be aqueous. The same is true for FeSO4. So what does K plus have? Well, it has charges of 1 plus and 1 minus, whereas FeSO4 has charges of 2 plus and 2 minus. So certainly the charges are higher between FeSO4 than they are between KCl. So that certainly gives FeSO4 some advantage in terms of having stronger forces that water is not going to be able to pull apart. From a size perspective, K plus and Fe2 plus are probably not all that different in size. K, potassium being an alkali metals on the larger end of things, Fe2 plus a slightly bigger transition metal in terms of the number of protons and neutrons that it has, but with those greater number of protons, it's actually going to be a little bit smaller than K plus is. So we're going to have a situation where they're about the same size when all is said and done. And then Cl minus, again, on the smaller end because it's not a particularly large atom. SO4, that's a lot of atoms. There's 5 of them, but they're all on the relatively small side. So while SO4 2 minus might be a little bit larger than Cl minus, it's not too much bigger, and the fact that its charge is substantially higher sort of is the more important factor. So FeSO4 has the stronger forces, and what we see is that a precipitate forms. And that means that KCl won't be a precipitate. There are certainly reactions where two precipitates form, but certainly early on it would have been a poor example to choose. And there's a series of logical tests we can kind of apply, and it starts with the ion-ion forces. Theoretically, we can also begin to learn our solubility rules, and we know that things like potassium always make aqueous compounds. They don't ever make the precipitates, but that's something that we'll kind of get to as we go. So what we would write for this overall reaction would simply be K2SO4 aqueous plus FeCl2 aqueous becomes, I guess we need 2 KCl's aqueous plus FeSO4 solid. There would also be other clues about which solid it was, things like color and things like that. So FeSO4 would have a color consistent with the iron 2+ cation. Potassium substances don't really have a color, or they're white as solids, so that would not be an indicator, again, that it's the potassium compound. It would be an indicator that it's the iron compound. This would be our overall reaction. If we wanted to narrow it down to the net ionic reaction, what we do is we look for the ions that don't change their phase and don't change their charge. So potassium started as aqueous. So potassium started off aqueous. It ended aqueous. Its charge is the same. So it actually did not undergo any sort of chemical change. In fact, it would simply be bouncing around as a dissociated ion at the end, the exact same way it was at the beginning. The same is true for chloride. So chloride was aqueous at the beginning. It is still aqueous here at the end, which means it also would have been floating around as a dissociated ion at the end, much as it was at the beginning. So neither one of those ions underwent any sort of change. So from a net ionic perspective, we would simply leave them out, and we'd say, well, this reaction is really simply the reaction of sulfate and iron 2+ colliding with one another and making the precipitate. And the K+ and the Cl- are really just there to help bring the sulfate and the iron to the dance, and then iron and sulfate dance, and potassium and chloride don't get involved. So this would be what we call the net ionic equation, and that's something that we'll work on a little bit more. Let's look at one more example, and then we'll call an end to this video. So let's look at another example. Let's look at the example of sodium iodide and lead 2 nitrate. Again, we know that there are now 4 ions floating around in water because this aqueous ionic thing means that they have already dissociated. So we have Na+ and I- floating around in water. They're both aqueous. And we have Pb2+ and the nitrate ion, and they're both floating around in water. And again, from a collision perspective, some of these ions are going to be colliding or attempting to collide, but they're going to repel each other. So we have the repulsion of the 2 cations, the repulsion of the 2 anions, so we're not worried about those. We also are not worried about the collisions between the particles that were already mixed together. So that doesn't really matter to us either, because we know they don't stick together, because if they did, they wouldn't be aqueous in the first place. So the only collisions that we might be concerned about are those between Na and NO3 and Pb2+ and I-. So the options for our outcomes then are going to be NaNO3 and PbI2. Now notice that's PbI2. We had to add this subscript here to make sure the charges were balanced. So what state of matter are we likely to encounter between these two? Well, Na again is 1+, NO3 is 1-, whereas Pb is 2+, and I is 1-. So we have stronger coulombic forces in the PbI2 than we do in the NaNO3, because their charges are 1+ and 1- versus 2+ and 1-. From a strict interpretation of the Coulomb's law formula, that would mean that the attraction between lead, iodide, all other things being equal, which they're not, because of the volume of these particles, but all other things being equal, the attraction of PbI2 is about twice that of NaNO3. So a stronger attraction for sure. And because it has a stronger attraction, even though it is slightly larger, it's not double the size, and so that will be the solid this will be aqueous. And again, as we learn net ionic equations, we'll learn that all the alkali metals are always going to be aqueous when water's around. So they cannot provide a lasting attraction. They're going to break up. So what we get would be the overall reaction of NaI plus PbNO3 2, making NaNO3. And if we look at balancing it, we'll have to deal with that in a second. There were 2 nitrates, so we're likely to need a 2 here. That gives us 2 sodiums. And then we're going to have PbI2, and that'll be a solid. And again, that works out nicely with the 2 iodines in both places. If we were to look at the net ionic equation, we would notice that Na and I are aqueous both times. They're aqueous here. Excuse me, not Na and I. Let's erase that as though it never happened. The Na is aqueous here, as is the nitrate being aqueous here. So the Na is still aqueous right there, and the nitrate is still aqueous right there. And so neither one of them does anything, doesn't undergo a change. Their charges remain the same, their phase remains the same. So the ions that we're concerned about that are actually involved in their action would be the 2 iodide ions and the lead 2+ ion. And they make the PbI2 solid. That would be our net ionic equation, which we'll talk more about again as well. All right, just a little introduction to this. We'll certainly come back to it as we move further on. The next video will look a little bit more intently at net ionic equations. I hope this is a good introduction. We'll certainly talk more about it in class. Still need my catchphrase to sign off, and in the meantime, have a great day, and we'll talk to you soon. Bye-bye.